Hey everyone, and welcome to Bayesian Machine Learning, A/B Testing in Python. This is a course I've wanted to do ever since I started making machine learning courses. A/B testing is one of the most important methods in data analysis. These techniques are applied everywhere in the real world, from medicine to marketing, from web page optimization to high-throughput online platforms. So whether you consider yourself a data scientist, a machine learning engineer, or an artificial intelligence programmer, you want to know about these techniques. In fact, you'd better know about these techniques. What you're going to learn in this course is that even people who do not consider themselves data people, like biologists, psychologists, and web developers, can and do apply these methods on a frequent basis. If you are a data person and you don't yet know about these topics, it's time to catch up. As we move increasingly toward an online world with millions of users on every platform, the need for a different approach arises. In the offline world, people run experiments. You might invite people into your office, have them fill out a survey, collect the results in an Excel spreadsheet, and then analyze them using the standard statistical techniques that have existed for decades. But what about today's world? In today's world, your experiments might not be surveys. They might be what a user does on your website. Your users don't ride the bus to your office. They download your web pages in fractions of a second. And you typically have so many users that putting them all into an Excel spreadsheet is simply impractical. In today's world, our technology is better suited for adaptive systems. Instead of the slow, small data methods from past decades, we want to move towards the fast, big data methods of today. And that's the kind of skill we will develop in this course. So what will you learn in this course? To be specific, we are going to take a very logical approach to A/B testing. In order to understand the new, you also have to understand the old. Understanding the old and the new side by side allows you to have a complete picture of all the techniques available to you and to compare their merits appropriately. We will start this course with a review of basic probability and statistics. Then we'll cover frequentist statistics and hypothesis testing. Now you might wonder, why are we talking about frequentist statistics in a Bayesian course? Well, this is all part of helping you have a balanced picture. If you don't understand one, you can't understand the other. Trying to learn Bayesian statistics without first being knowledgeable in frequentist statistics would be like trying to learn quantum physics without Newton. After forming a complete picture of the frequentist method, we will then move on to adaptive methods. These are the methods I talked about earlier, which are more appropriate for today's technology, such as online platforms with millions of users. This is a very different environment than inviting 10 people to your office to fill out a survey. So you want to keep these applications in mind as you go through the course. This is data science. This is statistics. These involve math and programming. However, it should be understood why you are learning these things and what you want to apply them to. These adaptive methods will culminate in the Bayesian approach to A/B testing. Based on experiments done by companies such as Yahoo, Google, and many online advertising companies, we know that the Bayesian approach is ideally suited to today's online platforms. To put it plainly, they work very well. I hope you are as excited as me to step into the big world of Bayesian machine learning. Remember, this isn't the end of your journey, it's just the first step. Thanks for listening, and I'll see you in the next lecture. In this lecture, I'm going to describe where to get the code for this course. The code for this course can be found on my GitHub page, github.com/lazyprogrammer/machine learning examples. The relevant folder for this course has been noted on this slide. In order to get the code, I would strongly recommend using the git clone command. I repeat, use the git clone command. If you're having difficulty using the git clone command, then as a last resort, you can simply use the download button. Here's what you should not do that I've seen students do in the past. First, do not go to File and Save As. This is not how you download code from GitHub. Secondly, please do not fork the repository. I update this repository very often, and you will miss these updates if you fork the repo. Furthermore, many past students have been confused by forked repos in the past, thinking they had found my repo when in fact they had found someone else's out-of-date fork. For the sake of your fellow students, please do not fork the repository, and if you have a fork, please either update it or delete it. Thirdly, if you don't know what Git or GitHub is, and you have no clue what I'm talking about, please educate yourself on why version control is absolutely 100% necessary for anyone who writes code. This applies whether you are in machine learning or you are an iOS developer. If you don't know why version control is not just necessary, but a superior way of storing and distributing code, please do a Google search and read about why this is true. Since I'm not here to teach you the basics of how to use a computer, you will have to take responsibility to make sure that you can install and use Git. And guys, remember, using Git is not some crazy new thing. Anyone with a job doing software development already knows how to use Git. It would be in your best interest to ensure that you have this basic skill. I want to remind you that being hands-on and engaging with the material is your responsibility. When it's time to code, you must code. You must put your hands on the keyboard and implement yourself the algorithms we learned about. I won't remind you that you should code, since I expect everyone taking this course to be mature enough and disciplined enough to write code when it's time to do so. Simply copying what I type is not encouraged. Simply downloading my code and hitting the play button is not encouraged. If you want more information, watch the lecture, How to Code by Yourself, which can be found in the appendix. You're also invited to watch the lecture, Should You Code Along, on my YouTube channel. The answer to this question is no. My motto has been, and always will be, if you can't implement it, then you don't understand it. I've even had some students implement what they learned in Java. Remember that the code I provide is merely a guideline. It doesn't matter if I use a different version of Python, if I use a different library, or even a different language. Be like our Java friend and code yourself. Please keep in mind that this course is always going to follow the same basic pattern. First, we discuss the theory, and then we discuss the code. Obviously, the theory involves the reasoning behind why and how an algorithm works. The code lecture is simply a translation of that theory into code. If you just remember this basic fact, you will never get lost or forget where you are in the course, because obviously this is pretty straightforward. First, we discuss what we are about to code, and then we actually code it. On this topic, please do not randomly skip around in the lectures. Students sometimes try this, and it's obvious when they have because they ask questions that were answered in previous lectures. The lectures are in the order they are in for obvious reasons. So unless you already know what you're doing, you probably don't want to jump around or treat the lectures like a reference. Continuing on this theme, let's remember that since you are the one doing the coding, you can choose whatever environment you like in which to do that coding. Sometimes people ask me, why don't you use Jupyter Notebook? Obviously, it doesn't matter what I use because it's in a video. The only difference between one environment and another, if it's in a video, is that it might be a different color, which is obviously irrelevant to you. I'm not saying you should do this, but if you did not want to write any code and you just wanted to run my code, you could simply copy and paste it into a Jupyter Notebook. Remember, there's no such thing as different versions of Python for different environments. Python code works the same in all environments. It doesn't matter if you use Notebook, PyCharm, Spider, Sublime Text, Atom, or Vim. It simply does not matter. You can code anywhere you like. The most important thing is that you do it in the first place. In this lecture, I'm going to give you a very brief introduction on how to succeed in this course. The longer version of this lecture can be found in the appendix, so these are just the basics. For most of you, what I say here will be obvious, but for some of you, you really need this, so listen carefully. If you've heard this before, feel free to hit the next button. First and most importantly, you must use the Q&A. You must use the Q&A, even if you think your question is stupid. Oftentimes, people ask me, where do I get the code, even when there is a lecture titled, Where to Get the Code. This is perfectly acceptable. You must use the Q&A, even if you don't know what question to ask. Your job is thinking of the right question. This is just like how it is in the professional world. If you are confused, you cannot just sit in your chair in the office and twiddle your thumbs. You can and you should ask your more knowledgeable coworkers for help. Just as your boss would find this unacceptable, so too would I. Oftentimes, the answer to your question will be a question. Just because you ask a question, this does not imply that the question will be answered in the way that you think it should. Obviously, if you knew the answer to the question, you wouldn't be asking it in the first place. How can this be? Remember that you are here to learn, not to memorize facts. If your question is, what will happen if I do this thing or that thing, the answer will often be to remind you of my motto, machine learning is experimentation, not philosophy. Obviously, the best way to figure out the output of a computer program is to run the computer program. The incorrect solution to this would be for me to run the computer program and then tell you what I saw. If I instruct you to do something, I expect you to follow up and do it. Guideline number 2, meet the prerequisites to this course. These have been listed twice in the course description for your convenience. In addition to reminding you right now, I will assume that 3 reminders is more than fair. If you disagree, please let me know in the Q&A and we can have a nice discussion about how you think this can be improved. So if you ever have a question like, what's this weird math symbol? Or what does this word mean? Or what does this line of Python code do? You should double and triple check that you meet the prerequisites. Sometimes students think they do when they really don't. For example, someone might say, yes, well, I have a PhD in economics. Nope, sorry, you do not get to invent your own prerequisites. The prerequisites have been listed clearly, and it's your job to follow them. On that topic, this is not a suggestion that you have to take my courses to meet the prerequisites. You can use whatever resources you like to meet the prerequisites. You can learn them in school. I don't care. It does not matter to me. The only time this gets a little thorny is when you take a course taught by a marketer who is posing as a data scientist and they spend the whole time talking about how cool and awesome the subject is while forgetting to actually teach you about the subject. So if the prerequisite is neural networks and you take a course taught by a marketer about neural networks, then you're probably just going to have to learn it all over again. As a small hint, if you signed up for a course on neural networks and they spent 2 hours talking about how to install Python and write for loops and if statements, then that's probably not the right kind of course. Moving on, recognize that academic versus professional is a false dichotomy. Have you ever asked yourself, what happens to an academic once they graduate? Well, they enter the professional world and they bring the skills they learned with them. So if you're ever thinking to yourself, there's too much math or there's too much programming when you're taking a course that's literally about math and programming, well, obviously that's a contradiction. Don't use the word professional as a euphemism for incompetence. Beginner versus advanced is also a false dichotomy. First of all, nobody can even agree on what beginner or advanced even means. Is a beginner a senior citizen who can't turn on a computer? Or is a beginner someone who has a PhD in physics and now wants to get into machine learning? Nobody else conforms to your personal definition of beginner and advanced, so these words are irrelevant. You either meet the prerequisites or you do not, and I hope that you do. Remember, I want you to succeed. Guideline number 3. It's your responsibility to test yourself to ensure you've learned what was taught in this course. I've said this before, but it's worth repeating again. Take all the algorithms you learn and implement them in code. These are the exercises in this course. If you count up every code example in this course, that's how many exercises there are. Remember my motto, if you can't implement it, then you don't understand it. One final bonus tip. I've been told that sometimes I talk too slowly. Other times I've been told that I speak too quickly. I would err on the side of slow since your fellow students come from all around the world and speak different languages. Obviously, we can't please everyone. Luckily, there is a speed changer right at the bottom of this video player. Personally, I like to watch my own videos at 2x speed, so perhaps you would like to give that a try. Hey everyone, and welcome back to this class, Bayesian Machine Learning, A/B Testing in Python. So here's a little story. At first, when I started this course, I assumed everybody already knew that A/B testing was pretty much the most applicable concept in all of statistics and machine learning. Years later, to my surprise, I've come to find out that this is actually not the case, and that there are people out there who don't know why A/B testing is useful. So if you don't know about the many, many real-world applications of A/B testing, then this lecture is for you. Alright, so there's no real order to these examples. They're just what I thought of
in the order that I thought of them. The first example is in medicine. Let's say you're a pharmaceutical company. You just made a new drug. You want to know if your drug works or not. If your drug works, then you can bring it to the market and make lots of money. The question is, how do we know whether or not the drug works? Well, let's say the drug is for reducing your blood pressure. Then we would like to answer the question, does this drug reduce blood pressure to a significant degree? To answer the question, you would have to run an experiment. In your experiment, you'll have two groups of people, typically called the control group and the treatment group. The treatment group would receive your drug, and the control group would receive a placebo. You can think of that as a pill that doesn't actually have any medicinal effects. It's like a sugar pill. Then, after the people in your experiment have taken their pills, you're going to measure their blood pressure. You're going to write down each measurement, and you're going to compare the outcome. Now, realistically, you might actually want to do something like measure the difference in blood pressure before and after taking the drug, but that's outside the scope of this course. In fact, there are a lot of details that are outside the scope of this course, but this is just meant to be an example, so just pretend for the sake of this lecture that they don't exist. It's important to remember that everyone is different. So for example, one person might have a starting blood pressure of 140, and after they take the drug, it goes down to 130. But for another person, they might have a starting blood pressure of 130, and they're in the placebo group, so they take a sugar pill, and their blood pressure remains at 130. In other words, there's going to be some overlap between the two groups. So how can we give you a definitive answer for whether the drug is working or not? Well, the answer is we need to do some calculations. Of course, these calculations are exactly what this course is about. So let's move on to the next example. Here's another example I think most people can relate to. We've all at some point tried to make a website. Perhaps you've even created a website to try to sell things online or to try and get users to sign up for your newsletter. In other words, your site has some performance metric. Typically, we call this a conversion rate. So for example, out of 1,000 people who visit your website, one person might buy something. Or out of 1,000 people who visit your website, maybe 10 people might sign up for your newsletter. In these examples, the conversion rates would be 0.1% and 1% respectively. Now, obviously, you want to be a successful businessman. And in order to do that, you must maximize your conversion rate. In other words, what's better than one person out of 1,000 buying something? Well, how about 2 or 3 or 4? So I want as many people as possible to buy my product. Now, of course, people buying a product on your website is highly reliant on how attractive and trustworthy your website is. If your website doesn't look good, or your website doesn't compel people to buy your product, or your website doesn't seem trustworthy, then people might avoid buying things from your website. Now you, as a businessman, decide that the best option for you is to hire a copywriter to write some content for your sales page. Your copywriter gives you several options, and it's up to you to decide which one you like best. In other words, you want to again compare these different options by considering which one gives you the highest conversion rate. Now this seems rather straightforward, but in fact there are some statistical details you want to keep in mind. Luckily, these are also covered in this course. Here's another example. Let's say you run a local business and you're handing out flyers to people in your neighborhood. You have 2 or 3 designs for the flyer that your designer gave you, and you want to find out which one is the best. Of course, best can be defined by the rate of people that call you back from each flyer. Again, the same techniques we discussed previously can be used for this task also. Here's another example. Let's suppose you run a cloud storage service. You need to order some hard drives, but you can't decide between Seagate and Western Digital. Of course, you know that with repeated use, your hard drives will eventually fail. The question is not if they will fail, but when they will fail. Now, obviously, you'd like if your hard drives could last as long as possible, so you can keep your costs down. Luckily, as you might guess, this is a job for A/B testing. As a side note, this is a very famous example, as the company Backblaze, which specializes in doing online backups, does a periodic report that lists out the stats for each hard drive that they've tested in the recent past. So what do all of these examples have in common? Well, hopefully you realize that the pattern was we needed to compare two or more items. Mathematically, each of these items will produce a number. And what we're usually looking for is one group to have a higher number or a lower number than the other group or groups. So for example, if we're measuring how long a hard drive lasts, we would want that number to be higher. If we're measuring blood pressure, we might want that number to be lower. The question is, how do we detect these differences? That's what the techniques from this course will teach you. Hey everyone, and welcome back to this class, Bayesian Machine Learning, A/B Testing in Python. In this lecture, we are going to discuss the question, what is Bayesian Machine Learning? And we're also going to talk a little bit more about what this course is about. One common mistake that I find students make is in their definition of Bayesian machine learning. We've all had some exposure to the concept of Bayes. This can happen as early as grade school, where you learn about Bayes' rule. Of course, that's not machine learning per se, but rather just basic probability. You might think you've encountered Bayesian machine learning before in the context of regularization. In models like linear regression, this corresponds to the maximum a posteriori, or MAP estimate. This is still not Bayesian machine learning, though. In college or university, there are actually some different fields in which you may encounter Bayes again. As you might already know, usually the statistics department is separate from the computer science department. And so you'll have the statistics folks in one area of the school and the machine learning folks in another area of the school. Each department has different priorities and different paradigms of thinking. They often even use different programming languages. Now, the reason I mention this is because while you may have had some exposure to Bayesian ideas in the past, your exposure was probably isolated to one of these two sides. So you may have studied Bayesian concepts from the perspective of statistics, but you wouldn't know about Bayesian concepts from the perspective of machine learning, which are very different. I think overall the lesson of this lecture is that you have to disregard your preconceived notions about what Bayesian machine learning is, and to remember that there are many faces on this vast topic. This lecture is going to give you a high-level overview of all the different areas you may encounter in your study of Bayesian machine learning and Bayesian statistics. The first area I want to talk about is what this course covers. This course focuses on the specific application of A/B testing, but there's also the undercurrent of Bayesian machine learning. Specifically, I would consider this an introduction to Bayesian machine learning because it introduces you to what it means to be Bayesian. We do this by comparing traditional frequentist methods to Bayesian methods. This is the same approach we took when we learned about the NumPy stack. The idea wasn't just to dive into NumPy for no reason. The idea was to compare the same operations in both pure Python and NumPy, so you could see the difference and convince yourself that there's a real reason why you would want to use NumPy. Similarly, for this course, we're going to compare these two approaches, and you're going to understand why you should take the Bayesian approach as opposed to the traditional frequentist approach. The Bayesian approach generally follows the rule, everything is random. To be more precise, everything is a random variable. Now, what do we mean by that? Well, let's take a simple distribution like the Gaussian. For the Gaussian distribution, we have two parameters, the mean and the variance. To give you a concrete example, suppose we want to model the height of all the students of our class using a Gaussian. So we want to find the mean and variance of the height of the people in our class. In order to find these values, here's what a frequentist would do. They would say, collect a bunch of data, meaning measure the height of everyone in our class. Then, using maximum likelihood estimation, we would find the mean and variance. To do this, we first calculate the likelihood function. Then, we maximize the likelihood with respect to the Gaussian mean and variance. Pretty simple, and you've probably done this before in your university probability class. The Bayesian treats this problem differently. Remember that we're following the motto, everything is a random variable. So in the frequentist paradigm, when we solve for the mean and variance, these both just give us a number. In the Bayesian paradigm, the mean and variance are random variables, and our job is to find their probability distributions. Now, of course, the details of this calculation are what this course is about, so we're not going to actually discuss that right now. But suffice it to say, that's the major difference between the frequentist and Bayesian paradigms. Instead of finding a number, our job is to find a distribution. And again, in terms of the big picture, this is your introduction to the field of Bayesian machine learning. It's a lesson on how to go from non-Bayesian methods to Bayesian methods. Now, of course, our learning doesn't stop here. If you go the statistics route, then a lot of your attention will be focused on sampling. There are many different kinds of sampling, such as importance sampling, Markov chain Monte Carlo, and Gibbs sampling. The idea behind sampling methods is to do numerical approximation of an integral. In fact, when some people talk about Monte Carlo, they talk about it as a technique of numerical integration rather than a technique of statistics. So this is interesting if you've ever studied other areas of machine learning, such as deep learning. With deep learning, you'll find that the main skill you apply from calculus is differentiation, which is often synonymous with the course Calculus 1. With Bayesian machine learning, the main skill you apply from calculus is integration, which is often synonymous with the course Calculus 2. Now, it's important to remember that this on its own is not a small topic. Sampling by itself could be one or more courses. That's how complex this topic really is. Now, there is a whole other direction we could go, the direction of machine learning and creating predictive models. Take a very simple model, such as linear regression. This is the first model we usually learn about when we learn about machine learning. It has a very basic equation, y equals w transpose x. In other words, our prediction is the dot product between the weights w and the features x. We call w the parameter, and our job is to find it given some data set, x and y. And so I think you know where we're going with this. We have to recall our Bayesian rule that everything is random. In the Bayesian paradigm, remember that the parameters are not just numbers, but rather distributions. So in Bayesian linear regression, for example, we're not interested in finding the vector w, but the distribution of the random vector w. We want to find p of w given x and y, where x and y is our training data. And of course, the same concept can be applied to many other classic machine learning models you already know and love. Some examples are logistic regression, neural networks, Gaussian mixture models, which are like a superpowered version of k-means clustering, PCA, also known as principal components analysis, and matrix factorization, which is used for recommender systems. The concepts of Bayesian machine learning can be generalized further to give us what are called Bayesian networks. Whereas the previous examples were specific models, Bayesian networks are a general model. Using BayesNets, you can create custom models with any kinds of dependencies you like. In this way, you are actually modeling causation. This, of course, can be based on your understanding of the system you're trying to model. So, for example, suppose I want to predict whether or not a student will pass my exam. We could have input features such as number of hours spent studying, number of hours spent playing video games, and number of hours spent sleeping. So if you used a non-Bayesian model like a neural network, you might just plug these into the input of the neural network and calculate your output based on a fully connected neural net. In other words, everything is connected to everything, and the neural network's job is to find the right weights. The Bayesnet method is to actually model dependencies. So you might say, number of hours spent playing video games actually has an effect on the number of hours spent sleeping. Then the exam score might depend directly on the number of hours spent studying and the number of hours spent sleeping, with only an indirect effect from the number of hours playing video games. So with Bayes nets, we can model these dependencies explicitly. Whereas with neural networks, we always use the same model and let the neural network figure out what the weight should be. Lastly, there are some very famous examples of Bayes nets, such as LDA, or latent Dirichlet allocation, which is an algorithm used for topic modeling. This is a separate example because while it's a specific instance of a Bayesian network, it doesn't have its roots in a non-Bayesian model such as logistic regression. So to summarize, I hope this lecture helped you understand the vastness of Bayesian machine learning. In many ways, it's just like deep learning. Today, I have 12 deep learning courses with more on the way. So there is no chance you can learn all of deep learning in just one course. Bayesian machine learning is similar, if not even more complex than deep learning. So while this course has the goal of introducing you to Bayesian machine learning, keep in mind that there are probably still 10 courses worth of Bayesian machine learning that you can still do after you learn the basics. I like the introduction to Bayesian machine learning in particular because it allows us to use the backdrop of A/B testing. A/B testing is one of the most, if not the most, real-world applicable concept in all of machine learning. So it's very easy to think of different ways to apply these concepts to the real world. This is opposed to, say, Bayesian logistic regression, where a common question might be, well, why don't we just use regular logistic regression? In that sense, it's a topic which is more appropriate for the 1%ers of machine learning, because you have to spend 90% more effort to get 10% more real-world application. In other words, if you're a beginner, then you probably don't want to go that far just yet, because you'll need lots of theory with not much return on real-world applicability. Whereas with this course, there is some theory, but at the same time, everything is super applicable to the real world. Thanks for watching, and I'll see you in the next lecture.